The top drawing here, I'll just recreate it. We have a circle, and whenever we have an angle, we're going to have two lines that meet. So we can create, say, a sector of a circle, like so. So we have something that we might call the radius, which is going to be what on this drawing? Okay, so it's a line from the center to the edge, so that we could call this the radius here, or we could call that the radius. So you can just draw a little arrow from the word radius over to the item that you want to identify as being the radius. What do we mean by the central angle of the circle? Okay, so where would it be on this drawing?
From like 12 o'clock down to maybe that ray that you drew would be
From here to?
That would be one of the rays of the angle.
Okay, right, so this right here would be the central angle of that sector of the circle, because it's measured from the center point. So again, you can take a little arrow and draw it to there. And finally, we have something that's called the arc length, which we're going to denote as being S. Who can tell me what the arc length is? Yes.
It would be the outside part of the circle between the two radiuses. If it was a minor arc, and then the other way around, it was a major arc.
Okay, good. So this right here is called the arc. And you're absolutely right, that would be the minor arc. Major arc would be going all the way around. We'll always be dealing with, well, not always, but we're always going to be dealing with the arc that's associated with the central angle that we've determined. Okay, and what do we mean by the arc length? What's that? How long it is, that's right. So the length, the measure of that arc is the arc length. Okay? So we're going to be relating these things. Of course, for a full circle, if we have an arc that goes all the way around, so it's as major as it can be, what is the measure of that angle, that central angle? 360, that's right. So going all the way around is 360. So for a full circle, we're going to go 0 to 360. Okay. So what I'd like you to do is at the bottom here, I have a few samples. We're going to identify some central angles. I want you to estimate. In some cases, you may be able to identify it exactly. In some cases, you might have to estimate it, but for the 6 circles given at the bottom, I'd like you to draw the arc for the central angle, or draw this little piece here. And then I'd like you to identify what that angle is. The only exception for this, for the very last one, the bottom right one, I'd like you to assume that you've gone all the way around and then come up to that line. So that last one I want you to draw it like this. Draw an arc that comes like this up to that line. And that's the angle that I want you to determine. There's a line like that. So go around all the way plus some. We're always going to start the horizontal line for today. If you're not sure you've gotten them all right, you're welcome to share with your neighbor. I mean, after you've answered, you can always check with your neighbor to be sure that you agree or at least approximately agree. Some of these are going to be estimates. Yes, we're going to start on the.
Oh, I started with this.
We're going to start on the x-axis and go from there. Sorry about that.
This is 360,
Yeah.
and then I figured that might be. You were 45 or
I know.
exactly in half.
Right,
so
that's why I didn't know if it was.
All these lines I drew by hand, so you know they are probably close to a particular angle, but maybe not exactly.
Plus and minus more.
Well, that's right, and that's why I'm telling you to estimate in some cases. Okay, does everyone have their degrees estimated? Okay, who can tell me what you got for the first one? Start off easy. Go ahead, Ruth.
90 degrees.
90 degrees. Everybody have 90? Okay. How about the second one? Remind me of your name?
Kristen?
Kristen. Thank you, Kristen. So 30? Okay, does everyone agree with that? It's approximately 30. That's what I was shooting for when I drew that. How about the third one? 180? Oops, sorry, Caitlin, right? Okay, good. Thank you, Caitlin. How about the fourth one? 240? Is that what everybody has? 230 you had? Yeah. Thank you, Stephanie. All right. The fifth one? 315, you think? Is that what everybody had? So you assume that was a 45-degree angle down below, splitting it halfway? I think that's a reasonable guess. That's what I had as well. How about the last one? Going all the way around and coming back.
405.
405, you think? Anybody else have anything different? 420 you had? Okay. Anything else? 410? Yeah, I think all those are reasonable. I didn't draw that one very well. I'm not quite sure. I think I was trying to make a 60-degree angle above the line, but I didn't do very well at it. So, so I was aiming for 420, but probably got closer to 410. Good. So, I mean, obviously it's not, if you keep in mind the main points here, that you have a 0 there, a 90 degree is a right angle, 180 straight across, 270, and then you get to 360 again when you come here. Everything else can be estimated in between. The ones that split in between, of course, are 45s that you add or subtract. So it's fairly easy to keep track. I just want to keep in mind that with angles, because we often will put angles inside of functions, and functions we like to have sort of an infinite domain if possible. So we can count angles as being going above 360, and we just count how many times we've gone around, add that number of 360s to the angle and to get the total. So that's how we get, say, a 410. Let's see. Let me just do one follow on here. Let's look at the first one again. Suppose we went around 3 times before we got to that angle. We went completely around 3 times and then went to that 90-degree angle? What would be the total angle in that case? $1170. I'll wait for someone else to confirm or deny. Anybody have a different one? Okay. Yeah, so 360 times 3 gives you 1080, and you add 90, 1170. I think that's correct. Good. Okay. Okay, very good. We're probably mostly familiar with those big angles from some of the extreme sports, I guess, like skateboarding or something, or they might do a 720 or a 1080. Even something in between. Very good. I have a question for you. See if any of you know or can speculate. Why do we measure angles in degrees? Seems like kind of a weird thing, right? We're splitting a circle here into 360 sectors. Seems like kind of an odd choice, doesn't it? Where did 360 come from? Anybody know or have any ideas? Have you ever wondered about that? Or is that something you think about? What's that?
Longitude, latitude.
What about them? They're in degrees, yes they are. But why would we split those into 360 pieces? Just because. What's that? Yeah, I mean, obviously we're splitting it into equal sectors because it is a circle, and that's an easy way to split a circle. Question is, why do we cut it into that many pieces and call that a special unit of a degree? You would split into 100. Wouldn't that make more sense? Or, when we cut a pie, you wouldn't give someone 1/360th of a pie, right? You give them 1/8 or 1/12 or something. Well, I think this really goes back to the fact that angles were first used in astronomy and first used to measure positions of things in the sky. And there are a number of astronomical objects that just happen to fit either 12 or 360, or very close to that. So for example, how many times does Earth spin in 1 year? 365, right? So you might say, well, why don't we split it into 365 pieces? Well, there's another thing that happens here. And the only reason I'm mentioning this, not because this history is really all that important, but it's going to sort of take us to the fact that there are other ways to measure angle, and maybe more natural or compelling ways to measure angle. And that's what's going to bring us to the idea of radians. But before we get there, I just want to sort of let you know where this convention came from. If you look at Jupiter, does anybody know how long it takes Jupiter to orbit around the sun? No? It's a good astronomy question. It's about 12 years. Okay? Which means that if you watch Jupiter in the nighttime sky, and the reason I'm focusing on Jupiter is it's one of the brightest planets. It was named after Jupiter, who was the king of the gods. It was obviously considered a really important planet. So if you watch Jupiter over a long period of time, you're going to see it move, say, from star to star over the course of many years. And it takes 12 years for it to come back to the same star it started at when you began watching it. So because a year is a natural category for humans to use, because that's how long it takes the sun to make a full circuit relative to the stars, and they watched Jupiter, and that took 12 years, they split the sky into 12 pieces. So that's where the number 12 came from that made it a special number. So when you combine the fact that 360 is a nice multiple of 12, and it's very close to the number of days in a year, it became natural to split the sky into 360 pieces. And more specifically, 1 degree is approximately the distance that the sun moves every day in the sky. And by every day, I mean not across the entire sky like the daily motion, but if you were to watch the position of the sun from day to day, it comes around and say, it would be lining up with a star right here one day. The next day, it will have fallen a little bit behind that star. The stars go, appear to move across the sky as well, and the sun falls behind a little bit. It falls behind by about 1 over 360 per day, and so the degree was sort of the motion of the sun on the sky, and so that made it a very natural. It made it a natural unit to use in astronomy. It's a totally unnatural unit to use in mathematics, which is why we use other units or other angle measures when we do angles on a more complex level. Okay. So if you take a look at page 2 now, I make a statement that we often measure angles in degrees, but that radians are a more natural measure. Let me close ink layer. There you go. Guess I'll just pop up these notes here, just so they're displayed. There we go. Okay. Okay. Now, when I say natural, I don't necessarily mean natural in the sense of compelled by nature. In a sense, the degrees were what developed naturally by doing science. But from a purely mathematical perspective, what we call the radian makes more sense. And the reason it makes more sense is it's a natural unit of the circle. So what do we mean by a radian? Well, what we mean by a radian is the following. Suppose we took our circle, and it has a radius. And suppose we took that radius and we stretched it around the circle as far as it would go. You can see that the radius of this circle is about that far. So if I took it and started stretching it around, it might end up somewhere like here. The radian is an angle measure in which the arc length is equal to the radius. So the arc length of the radian is equal to the radius of the circle. What's that? It's not equilateral. Right, because equilateral is where you take the straight line radius across like that. That would take you up a little higher here because you're going straight. We're taking the radius, but we're curving it so you don't get quite as far. But the angle that corresponds to that radius curved around the arc is called a radian. Okay? It's not very intuitive for us because we've been brought up to think degrees, 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 degrees. And it's also not a very small unit. You can see it's taking up a large chunk of the circle. So it's not necessarily the first degree angle measure you would think of if you wanted to measure on a practical level. Because usually, oftentimes, we measure smaller increments. Yeah?
So then what's the difference between the minor arc that's there and what you're calling a radian now, which is stretched across that way?
Okay, so
You said that
I have to think about this for a second. People can correct me if I'm wrong, all right? Because I may be. I don't really think in terms of that terminology of minor and major arc. But when I think of the minor arc, I think of an arc that is less than 180 degrees that is bounded by that central angle. If you have your central angle larger than 180, I would then call that a major arc. So in my mind, the distinction between minor and major is whether your angle is less than 180, 180 degrees, or greater than 180 degrees. Now this piece of what I've drawn here is a minor arc because the angle is clearly less than 180. But if I had some number of radians, obviously it would go farther around, and then it could become a major arc. So
I think he's confused because your minor arc that you just happened to draw by chance is about the size of a radian. And that's not what you intended. The minor arc.
that's not what I intended, and it's merely approximate. Yeah, there's
So
it just so happened that I happened. Just when I was randomly drawing, I happened to draw something that was on the order of a radian for the central angle. That was purely coincidental.
But if I were to draw that on my paper, it would still be.
Yeah, you could, I mean, that's right. If I drew something up like this, obviously that's a bigger arc. That would be more than 1 radian because the radius won't fit around that far. Okay?
Starting from what point? You're just talking.
I'm always starting from the x-axis here. We're always going to measure our angles, at least today, in this class, we're always going to measure our angles from this x-axis. Okay? Sorry for that unfortunate coincidence. I didn't mean to confuse anyone by that. Okay. So the first thing I want to impress upon you is the radian is a unit that's determined by the fact how far the radius will stretch around the arc. It's a natural unit, mathematically speaking, but it does give you a unit that's sort of large. Okay? All right. What's nice about it, however, let me draw for you a different angle that will not be exactly 1 radian. So our arc length is S, and our radius is R. What's nice about this definition is the following. That if I want to measure, and this is written in your notes, but I'll write it down here. If you want to measure an angle in radians, all you need to do is to take the arc length and divide it by the radius. Taking the arc length and dividing by the radius gives you the angle in radians. And the reason why this formula works is because for 1 radian, the arc length is equal to the radius. So that S is equal to R in that case. So if you plug in R for S, you just get R over R, and that gives you 1 for theta. I see some people have some questions or uncertainties. What I've said is perhaps not completely clear. So let me ask if someone has a question about that. Susan, are you okay? Does that make sense?
I think so,
You think so?
yeah.
Okay. Remind me of your name again?
Sandra.
Sandra.
I'm, yeah, I'm waiting for the examples with like numbers.
Okay.
But I think I'm good, thanks.
Okay, so this is going to be a really, really important thing. It's a pretty simple formula, and it's a really, really important one. Because what it tells us, and the reason why we use radians, is that all we need to know is that arc length, how far along the circle you've gone, and the radius, and then boom, you automatically get the angle that's subtended by that arc. So this is the length of the arc that's subtending that angle, and the number that you get is the angle in radians. It's not going to be the angle in degrees, it's the angle in radians. Later on we can translate into degrees if we want to. Okay? All right. I thought we might try a little activity just to get a sense of how big a radian is, and not just one radian, but multiple radians. So I have a series of circles here. I'm going to give one to each pair, I think, because we have 2, 4, 6, 8, 9. Okay, we'll maybe have pairs, and then one can be a triple. Here's your circle.
Thank you.
Okay. And I'm going to give each of you a ruler. I think hopefully that's big enough to go across the entire circle. Mhm. Okay. Now, because the whole idea here in measuring radians, we are always measuring the number of radii, or radiuses, that will stretch around that arc. The only way to really stretch something is to have something flexible. What we're going to do is use string. So your job here is to basically figure out when I give you your radian measure, okay, you're going to have to figure out how long to make the string, and then you're going to demonstrate by stretching it around there, okay? So I think for now we'll just do whole numbers of radians. I'll give you, what number of radians do you want to measure? 1, 2, 3, 4, 5, 6, 7, 8. How many do you want to do?
How many do you want to do?
Yeah.
How many do you want to do?
I mean, which value of radians do you want to demonstrate?
Oh, I don't know. Okay, 5.
You're going to do 5?
Yeah.
Okay. So you have to figure out how to demonstrate 5 radians. What do you want to do?
We'll do 2.
You want to do 2 radians? You want to do 3 radians? Okay. So I think we have 2, 3, 4, and 5, right?
You want somebody to pick something bigger than 6.
Man, I think this is fine. Well, this is fine. Okay. So figure out how to demonstrate your number of radians on that circle. Okay. And when you're ready to come up and cut the string to whatever length you want, you may come up and do that. We have the scissors and string up here. I will do 1 radian since no one chose that one. And do remember, your arc is the outside of this metal ring. So any measurements you do have to be to the outside of the metal ring. Does everybody have their strings cut and demonstrated? Didn't hear anyone saying no. All right, why don't we take a look then? I'll start us off because I did one radian, right? Okay. So let me just demonstrate as well as I can here. My string is 1 radius long. And I have to take this radius and stretch it along the circle. So if I take it here, my two fingers, so a radian is the angle that corresponds to that arc, okay? Which is about what we had drawn on there. It is a good visual. You can see it right along the outside edge there, okay? That gives you a sense. I mean, it's a good-sized piece of pie. If you offered someone a piece of pie the size of a radian, they would say, yeah, that's a good size, I'm hungry, right? It's not one of those little wimpy degree ones. So you can offer people radian-sized pieces of pie and they'll be happy, all right? So let's try to draw it on here. I'll go back to what I had. I think, yeah, actually, what we can draw them on here, approximately. So it's going to be about maybe to here. So that's about 1 radian. Okay? All right, who can show us 2 radians? Okay, show us. Why don't you come up here and show everybody?
Wouldn't 2 radians just be the diameter?
Oh, yeah, prove to us first that you have 2 radians worth of string. Hold it up to the circle so we can see. All right, I believe that.
Like that.
It doesn't appear to be measured.
Okay, so can you see if you can orient it the way we, yeah, see, the bottom of the string should be at the horizontal line, more or less, okay? All right, so is this going to about 90 degrees, or is it past 90 or before?
90.
Past 90?
That's pretty much perfect.
Okay, yeah, so I think the string, as you stretch it around, goes past 90. So 2 radians takes you more than a 90-degree angle, okay? So let's see if you guys could tell me where to put the second radian here. Where should I put it on this circle, more or less? We know it's past 90. Tell me when to stop.
Good enough. Good enough.
Right about there?
Yeah.
Okay. Okay. Who's our 3 radian demonstrator? Okay, why don't you guys get up and show us? First, prove to us you have what would create 3 radians. Can you show us, compare with the circle? Okay, so it looks like a diameter and a radius, which would be 3 radii. Good. Okay, so it looks like it's close to half a circle. Is it all the way, I mean, is it 180 degrees, or is it more or less than that? I think it's a little less, just slightly less. Yeah, okay, good, very good. All right, so tell me how far we should go then. I'm going to move my finger. Shh, tell me when to stop. Right about there? Okay, 4 radian demonstrator. So this should be how many radii? 4 radii. Okay, 2 diameters. Good. It's believable. It's not easy to do, is it?
Got it in the x-axis position.
Okay, good. So now we're well past 180, but it looks like we're falling short of 270, right? Yep. So that's 4 radians. Good. All right. So tell me when to stop then. Right about there. A little bit more, you think? There? All right, well, we'll see. Okay? And we need our 5.
This is 5.
We did a strategic move to make sure we had the exact center.
Very good.
So we went, there's, oops, sorry. There's 1. So there's 1 diameter. I'm a little off. I pulled it too tight. There's another. And there's almost to the radius because we lost them in the bend.
Yep, sure. Okay, good. Very good.
And then
I believe it.
Start at here. We'd make it to. Is that about 3 spots here?
Okay, so is that making it past the bottom? Is it past 270?
It is, isn't it? I can't see it.
It's
but I
just,
think
I think it's just,
it should be past it, right?
yeah. Well,
Is
wait,
it?
because it is.
Okay.
Well, if we went around the inside, which is where we actually measured.
Oh, you measured the inside?
We should have, shouldn't we have?
You should have measured to the outside because we're using the outside as our arc.
Okay.
So maybe your string is a little
So it
bit
might be
short.
a little bit
A little bit
That's
short.
what our difference is.
That's
Okay.
okay. That's okay.
Either way, it should go past.
It should go past 270. I think it should. Good. All right, so tell me how far to go then.
Oh, way past.
So let's try it again. Tell me when you think I should stop.
About there.
About here? This is going to be sort of approximate. What happens if we go to 6 radians? Where's it going to be? Goes all the way back up? Well, if our drawing is accurate here, look at the size of this arc. Is this one bigger or smaller than that? It's bigger by quite a bit, isn't it? So it's not going to quite make it. It's maybe going to make it up to there. So this is going to be 6. Okay? What if we get to 7? 7 is going to be past that 0 line. So how many radians do fit a circle? It's not 6 and it's not 7, it's something in between. 6.28? What? 2 pi. That's right. It turns out that there are 2 pi radians. It's not an even number. It's not an integer. It's that sort of funky 2 pi number, 6.28, 6.29. How do we know that? Well, if you take a look here, so it says for a full circle, the arc length is equal to, of course, what do we call the outer arc of a circle? What's the measure of an outer? The circumference. So since the length of the arc divided by the radius is always the angle in radians, the length of the arc divided by the radius, for a full circle, you're going to have the circumference, which is the length of your arc, divided by the radius. And what's the circumference? The formula for circumference? 2 pi r. And of course the r's cancel, and you're left with 2 pi. Okay? So there are 2 pi radians in a full circle. So whereas degrees go from 0 to 360, radians go from 0 to 2 pi for a full circle. Okay? Okay. So, bottom line is radians are a measure of angle that's motivated by the geometry of a circle itself, not motivated by observations that we do out in the world. And it is the arc length equal to the radius. And it's a pretty big measure of angle. What that really means is when we measure typical angles we're going to have, the number of radians is going to be relatively small. We're not going to be measuring things like 10 or 20. We're going to be measuring more things more like 0.1 or 0.2, some fractions of a radian oftentimes when we measure angles. Okay? So what we'd like to do is to make a relationship between the number of degrees and the number of radians so we can calculate one from the other. That's sort of a useful thing to do. So how are we going to do that? Well, the simplest way is to make a ratio, a mathematical ratio. And that's what I describe in words in the notes. You scroll down here. Oh, by the way, before I do that, let me just pop this up here. There's a little nice little demonstrator here on Math is Fun. It's nothing like a little little active app here to make things fun. Here we go. What happened? My browser has been upgraded. I want this. There we go. So you can drag the points here to demonstrate an arc length. So if we wanted to make an arc length of 1, you just move this around until it reads something close to 1. And that would be an arc that is 1 radius long. If we go to a 2 arc length, drag it around. Right about there, I guess. And that would be 2 radii, 2 radians as well, and so on. We can go to 3. So this is a nice way to visualize it as well. Although I thought the string was probably a more manual, physical way to do it. But you can do it easily with this as well. Okay? Okay. So you do have the link there if you want to use it in the future. Okay. So what we're going to do is we're going to make some ratios. We can compare 2 items to each other, and that will have to be equal to the comparison of 2 similar items. So what I want to compare is the size of the angle to the size or the angle of the full circle. So if we make this comparison, the size of the angle to the angle of the full circle, basically we're asking ourselves, what portion of the circle have we used up? How much of our piece of pie are we taking up of the whole pie? And we can do this in any units we choose. We can do it in degrees. We can do it in radians. We can do it in both and set them equal because that ratio has to be the same no matter what units we use. So that's what I've written down right here. You can see that our theta, which is our central angle, measured in degrees, that's the piece that we've cut out, over 360, it's going to have to equal the same ratio if we do it in radians. So that's going to be equal to the theta in radians over 2 pi, which is the going all the way around the circle in radians. What I would like you to do is to solve this for calculating the degree in, the angle in degrees in terms of radians, and then vice versa, calculating the angle in radians from degrees. So I would like you to write down those two formulas based on what's written here. I'd like you to solve for theta degrees and then solve for theta radians and write it below.
We're supposed to go right to the bottom.
You can fill them in if you want, but I mean, I did want to just check, once people have their formula, I just want to check what formulas they wrote down to make sure that we're all good. Did everybody write down your formula for getting theta in degrees and a formula for getting theta in radians? Everyone's done that? Yes? Okay. All right. Who can tell me what you wrote down for getting theta in degrees? Good.
360 equals the, whatever the radian would be over 2 pi.
Okay, say it again.
Theta over 360 equals like 1 over 2 pi. If it's 1 radian.
Okay, theta over 3, so by theta you mean theta in terms of radians.
Yeah.
Okay, so let me write that over here. Theta in terms of radians. That's the number that you're going to plug in, right? Like you've been given theta in radians. And so what's out here? That's the conversion factor?
S equals R.
I'm sorry, Susan. If
It's the S weight.
what's that?
It was the S over R.
We want to get something where it says theta in degrees is equal to some constant times theta in radians. Right? No? Yes? Confusion?
I did X over 360.
What's that?
That's what I
X
did.
over 360.
Oh, you're using x for the theta radians?
Well, that's
Theta
degrees.
Yeah.
Oh, theta degrees. Okay. So you're calling this x?
That's X.
Yes.
Okay. That's fine.
Over
Oh,
360.
so you want us to put the 360 on the other side is what you're looking for?
Yes, I would like you to get this by itself or this by itself.
Sorry, we were misunderstanding.
I did not express myself clearly. That was my fault.
Yeah,
What's that?
That's a proportion.
Yeah, but then he wants the next step, is what he. So you want the degrees equals 360 theta divided by 2 pi, is that it? Wait, I don't know if I have it written. Let me do it again.
Okay, what would we get from this formula here? If you look at the whiteboard, I'm circling it with the with my cursor.
Right.
If we get theta in degrees all by itself on the left-hand side,
Yep.
what's going to be on the right-hand side?
360 radians divided by 2 pi.
360 over 2 pi times the angle in radians. How might we simplify that?
Oh, 180 times 3.
Okay, so you might have 180 over pi. Would be one way to do it. Who wrote it this way? Anybody? Okay, Ruth, you did. Okay, you did. Jim, right? Eric. I'm sorry, Eric. You're Jim. Jim, Eric. Okay. Did anyone write this differently?
I just didn't reduce it.
What's that?
I just didn't reduce it.
Oh, okay, so you had 360 over 2 pi? Okay. Okay, we could also write this as a number, because pi is just a number, right? So you could write it as a number in degrees. What would that be? $57 point what?
3. Unless nobody's open.
Okay? So you could also write as 57.3. But I think, from my own perspective, I think it's easiest probably to remember 180 over pi. If you go half a circle, it's pi radians. And if you remember 180 over pi, it's sort of straightforward. You can always plug that into your calculator if you remember that. It's a little harder to remember a number like 57.3. How about getting theta in radians from theta in degrees? How do we express that? Just flip it. Okay? So we could write as pi over 180. Okay? So these are the two formulas. I mean, it's really the same formula, just sort of flipped on the this part is flipped to the other side. But these are the two formulas you could use to convert from one to the other. So what I would like you to do, if you haven't done this already, is to calculate the value in radians of the various radians into degrees. Compare what you get here to what we got on our circle. Does it make sense? Does it agree with what we drew on our circle? And then you can also convert, do this practice here. Do these conversions down here. Okay? So I'll give you a few minutes to work on that while I collect our rings.
I have all this expressed.
What's that?
I have it all done.
Oh, that's fine.
Did it express the way
That's
you-
fine. No, that's okay.
Is
If you-
there a
if you-
symbol for radians? Like, or do you just write it out every time? Like, how do you write 2.27?
Yeah, if you want to avoid confusion, I would just write out the word radians.
Okay.
Or you could write out RAD,
Okay.
which is what they sometimes have on a calculator.
Okay.
But strictly speaking, you should really just be writing theta, or whatever your symbol is for the angle, equal a number, and that number is the number of radians.
Okay, so it doesn't really need.
If it's in degrees, you always put the little
Right.
degree
So it
circle.
doesn't really need it.
Doesn't really need, it's not really a unit to speak of. It's really just a number.
Okay.
Has everyone calculated angles, or you're still working on them, or conversions? Okay, so why don't we just go in order here? 1 radian is 57 point what? 3. Okay, 57.3 degrees, more or less. 2 radians. Okay, 3 radians. 171.9, and 4 radians, 229.2. So I think if you look at these degrees, which we sort of have in our head what they mean a bit, and look at the circle that we drew, you'll see that it corresponds pretty well. For example, the 171.9 is just short of 180. So it takes you close to, but not quite to, half a circle. Okay, how about 130 degrees? How did you write that? 2.27 radians would be one way to write it. How else might one write it? What is it? 0.72 pi is another way to do it. So let me just emphasize, because pi is a natural number to sort of show up for radians, we can just keep the pi there if you want. It gives you less to calculate. You can just divide your theta by 180 and then express your radians in terms of pi. I just want to let you know, not that this is all about the test, but on the test, for example, they give you radians both in terms of pi and also not in terms of pi. So, you have to be able to write it both ways and be able to deal with that. I will say, for a practical matter, mathematically speaking, we usually write it with the pi in there. We don't care what the actual final number is. We just want to know what portion of pi it is. because that makes the most sense when we start using trig and plugging into sines and cosines. But you can write it either way. How about minus 32? Negative 0.56 radians, okay? And in terms of pi, what would it be? Minus point. Okay, 178 or 18. Yep, that would be fine. How about 80 degrees? You can just call it out as the spirit moves you. 1.4 radians, good. In terms of pi's, 0.44, good. 230 degrees, 4.01 radians, good. Also 1.28 pi.
Can you leave them as like 4 pi over 9? I mean,
Say that again?
If you're doing them in terms of pi, can you leave them as 4 pi over 9? I mean, is that
Yeah, it's okay to write it as a fraction as well. So sure, yeah, you can do that. Yeah.
Just explain that one of the advantages of a decimal is that you know what part of a pi it is.
Yes. Yeah, that's right. It sort of depends on whether you think more in fractions or think more in decimals. I'm a very decimal thinker.
So are the kids. 'Cause
So are the kids,
they
yeah.
hate fractions.
They hate fractions. I hated fractions when I was a kid.
I force them sometimes to use
Yeah.
fractions. So mad at me.
Fractions are the devil. All right. 3 pi, you'll see, for number 5, I wrote 3 pi over 7 radians. What's that in degrees? 77.1. Good. 10 radians? 573 degrees. Good. Pi over 16? 11.25. And 5 pi over 6? What is it?
150.
150 degrees. Good. So you can see the conversion from degrees to radians or radians to degrees is pretty straightforward. I mean, you do have to sort of remember the formula, but keep in mind that even if you don't remember the formula, it's not too hard to derive. Just remember the radians. How many radii are we fitting along? And you can do that proportion of 180 to pi. Okay, good. Now, this was the point at which we were going to measure the angular size of the sun, but we can't actually see the sun right now, so we may do that next time. If we don't, that's okay too. Let's see, we have...
Do we not see you again till Thursday?
yes, I think Thursday is our next time. So let me think here what we can... well, I'll tell you what. Why don't we get started? I will give out the mission to Pluto thing. And you guys we can work on a little bit now, and then we can finish it on Thursday, or you can even do it on your own time if you want to do a little extra homework. I'm going to give you a good example of how this might be used. The idea of radians and angular measure. How it's used not just in sort of basic science you might do in school, but very advanced NASA type science. So as you know, we've just sent the New Horizons spacecraft past Pluto. Let me just draw a little drawing for you here. One of the things that the New Horizons spacecraft did for us was to really pin down precisely the size of Pluto. We didn't have a good idea of exactly how big it is. We knew approximately maybe within 10%, but we didn't have it pinned down within a few kilometers, and now we do. But how does it do that? I mean, we didn't actually land on Pluto. We didn't drive a rover around with a giant string to get how big Pluto was. You have to measure it somehow, and the way you do that is with photographs. But the photographs themselves don't come with a scale on them. You have to determine the size of Pluto from those photographs. And how do you do that? Well, you do it using angles. So let me draw a little picture. Here's Pluto, let's say. That's not a very good Pluto, but we'll go with it anyway. And here's the New Horizons spacecraft. And the New Horizons spacecraft is taking a picture. And the only thing that the New Horizons spacecraft knows about this picture are the angular sizes that it's getting. So when it gets a picture and it's on the CCD detector, it knows how many degrees, I shouldn't say degrees. It actually knows how many radians. It knows what the angle is across that picture. And based on that, it can figure out the actual size of things. So let's see how this would work. Let me draw a little sector here. And we have an angle that we're going to measure in radians. That's what we're getting from the picture. And we have a distance away from the object, and that's r. And the last piece that we need, that we're looking for, is the diameter of the planet. Now you will notice that I drew the diameter of the planet as being a little arc, the arc length, s. We know that the diameter of the planet is actually a straight line that cuts through the planet. It's not a curved line. But for the kind of angles we're dealing with, you can't distinguish a curved line from a straight one in terms of what you're measuring, because a very small angle, you can't, well, like I said, you can't tell the difference between a curved arc and a straight line. So if we were to measure the arc length here, we can get the diameter of the planet. So let's take a look. We had the formula that theta in radians is equal to s over r, right? The arc length over the radius. We had already written that down. All you need to do is take the arc length and divide by the radius, and that gives you the angle in radians. You can also go the other way. If you know the angle in radians and you know the radius, you can calculate s, the arc length. So that's just, we just have to multiply both sides by r. You can see that the r's cancel on this side. And so we're left with this formula here. So you can get the diameter of the planet, which is going to be the arc length, by taking the angle that it makes on the picture times the radius, which is the distance away that you are, and then calculate it. Okay? Believe it or not, despite all the complex technology and the complex math that all the NASA scientists are using to send a spacecraft like New Horizons to Pluto, the actual measurement of Pluto's size is no more complicated than taking the angle in radians and multiplying by the radius, which is the distance away. Okay? So what I'd like you to do is take a look at the sheet that I've given you here. First of all, we have to know how far away we are from Pluto. How far away are we in this photograph? 280,000 miles. It's written right there. Okay? Now we're going to be using kilometers because science is metric, so we're going to be all metric. So 450,000 kilometers. The only other thing we have to do is figure out what this picture is, the picture of Pluto, how many radians this is. Does anybody know how we might go about figuring out how many radians Pluto is in this picture? On this picture, it is some size. But that size is going to correspond to some number of radians. Does anybody know how we might do that?
So you take the arc length and you divide by the radius and the theta?
Okay, we could do that. That's using this formula right here, taking the arc length and dividing by r. In that case, the arc length would just be the distance across we would measure on the page. The only problem we have with doing that is that we don't have an R. We don't know how far away on the page we need to be. We know how far away the spacecraft is, but we don't know how far away from the page you would have to be to do that. So we don't have that R value. It's a good idea, but that doesn't quite help us here. There is some information on this page that tells us how big this is in degrees, or it allows us to figure it out. There's a scale on the bottom. What does the scale on the bottom tell us? What information are we given? FOV would be field of view. That tells you how far across the detector can see. Okay, let me just point you to a few. We'll calculate this next time because I do want to let you go so you can get to your next thing. But if you notice on the bottom, it says that the picture is 1920 by 1080 pixels. It means there are 1920 pixels across the entire picture, not the picture of Pluto, the entire black screen. 1920 pixels. You will notice on the next line up, it tells you what the resolution of the camera is. It tells you how many milliradians. What's a milliradian? 1,000th of a radian. So it tells you how many milliradians there are per pixel. So you can figure out how many milliradians there are across the entire picture, and therefore figure out how many milliradians there are across the picture of Pluto. Right? If you know how many milliradians there are across this entire black rectangle, you can get the number of milliradians across Pluto by measuring. Okay? So we're not going to do that now. We'll do that next time. But this will give you a good idea of how you would apply this idea of radians and angular measure to a real scientific measurement. Okay? If you want to try, I laid out very briefly for you how you would do it. If you want to give this a try, all you need is a ruler and your calculator, and you can try to do it before you come on Thursday. Okay? We have a big gap between now and our next class. Try doing it, and we'll definitely do it when we get in class next time. Okay? Okay? Any questions? By the way, you can do the same thing on the other side with Pluto and Charon and the distance apart that they are. But the simplest thing is just to try the first size. Before I let you go, I just have one last question to ask you. I just want to see a show of hands. How many people feel comfortable, by comfortable I mean you could solve problems with it, with trigonometry? Raise your hands. And how many people feel that, actually, I'm not going to ask you to tell me what this number is, but how many people think that they could tell me what this is if I were to ask? Raise your hands. Only Ruth. Okay, that's fine. I just want to make sure that I expect when the high school teachers get in here, they're going to know their trigonometry really, really well, and I won't have to dwell on it all that much. I see that you guys want me to dwell on it, so I will. We'll be talking about some trigonometry next time.
The guy we had last year for it was really very good.
Yeah, Chris.
But yeah,
Chris Catone did it.
He was great,
Yeah.
but